Chelsea walked into the shop on a Thursday afternoon with a folder full of receipts and a 2014 Subaru Outback that was still shifting rough at idle after 3 separate visits to another repair place. 2.5-liter FB25, naturally aspirated, 152,000 miles, one owner from New, Des Moines, Iowa. Her list of complaints when she'd first taken it in 6 weeks earlier had been 3 items. Rough idle at stoplights, especially after the engine warmed up. A faint but persistent oil smell inside the cabin when she'd been driving for more than about 10 minutes. And a check engine light with a stored P0171 code, Bank 1 Lean. Her previous shop had run through what I'd call the standard misdiagnosis chain. First visit, they scanned the codes, saw the P0171, and replaced the mass airflow sensor. $220 for the part, $90 labor. Light came back within a week. Second visit, they cleaned the throttle body and reset the idle adaptive learn. About $150 in labor. Rough idle unchanged. Third visit, they told her the valve cover gasket was seeping and the oil vapor smell was coming from that. Replaced the gasket, added a new PCV grommet at the same time. $480 in parts and labor. Rough idle unchanged. Cabin oil smell reduced but not gone. Total across 3 visits, about $2,400. Stay through to the 15-second warm engine test at about 11 minutes in. That's the exact test I use before touching any diagnostic tool on a rough idle car, and it costs $0 and 0 parts. If Chelsea's previous shop had run it on visit 1, she'd have paid me $80 instead of that other shop $2,400. Near the end, I'll also show you what my own 2020 Tacoma looked like at 68,000 miles, running the same test preventively. Because reactive versus preventive on this one $9 part is the difference between a 15-minute maintenance habit and a 6-week diagnostic cascade that eats your monthly budget. None of those repairs was wrong on its face. The MAF sensor did have some contamination on the platinum wire when I pulled it out to look. The throttle body did have deposit buildup. The valve cover gasket really was seeping. Most Subaru FB25s past 140,000 miles do have some seep. All 3 of those things could reasonably be replaced on the schedule she was on. But none of them was the actual cause of the rough idle or the P0171 or the cabin oil smell. The actual cause was a $9 plastic check valve on the top of the intake manifold that had gotten so clogged with sludge and carbon that it was no longer functioning as a check valve at all. Replacing it took 15 minutes and $18 all in with a new gasket. I want to walk through why this happens, because it's not unique to Chelsea's Subaru. This exact cascade of symptoms and this exact misdiagnosis pattern shows up on cars from almost every manufacturer. And the diagnostic tree that most independent shops use tends to check the PCV valve dead last, if at all. The PCV valve, positive crankcase ventilation. It's one of the smallest, cheapest, most consequential parts on any modern gasoline engine, and it exists to solve a problem that most drivers have never thought about. Every gasoline engine burns a mixture of fuel and air in the combustion chamber above each piston. But the seal between the piston and the cylinder wall, the piston rings, is not perfect. It can't be. If the rings sealed 100%, the friction would destroy the engine within hours. So the rings are engineered to seal something like 98 or 99% of combustion pressure, and the remaining 1 to 2% leaks past the rings and down into the crankcase, the lower part of the engine, where the crankshaft and oil pan live. That leaked combustion gas is called blow-by. It's a mixture of unburned fuel vapor, partially combusted hydrocarbons, water vapor, and combustion byproducts. On a healthy engine at normal load, the volume is small, but not zero. On a high-mileage engine, or one with worn rings, the volume can be significant. That blow-by has to go somewhere. If you sealed the crankcase completely, pressure would build up inside it as blow-by accumulated, and that pressure would eventually force oil past every seal in the engine: the front main, the rear main, the valve cover gaskets, the timing cover, the oil pan gasket, everything. Before 1961, the standard solution was to vent the crankcase directly to atmosphere through a small tube called a road draft tube. Blow-by gases just dumped out under the car. Environmentally terrible, mechanically simple, worked fine. Since 1961, federal regulation has required a closed crankcase ventilation system. The blow-by has to be captured, routed back into the intake tract, and reburned in the combustion chamber. The PCV valve is the check valve that controls this routing. Here's how it works when it's healthy. The crankcase connects via a hose to a small port on the intake manifold, downstream of the throttle plate. At idle, when manifold vacuum is high, say 15 to 18 inches of mercury below atmospheric, the vacuum pulls blow-by gases out of the crankcase through the PCV valve into the intake stream and into the combustion chamber. The PCV valve is a spring-loaded check valve that opens under vacuum and closes under pressure, preventing intake pressure or backfire from being forced backward into the crankcase. Under acceleration, when manifold vacuum drops toward atmospheric, the PCV valve partially closes and reduces the flow rate. Under a backfire event, the valve slams shut instantly and prevents ignition from traveling backward through the intake. Simple mechanism, $9 part, absolutely critical to engine longevity. A note on modern direct injection engines, because these are the ones where PCV problems have gotten more expensive and harder to catch. On a port injection engine, the intake valve gets a continuous wash of fuel every intake cycle, which dissolves and carries away most of the oil vapor that would otherwise settle on the valve back. On a direct injection engine, GM Ecotec LTG, Ford EcoBoost, most current European turbocharged 4s, most current premium Japanese engines. Fuel is injected directly into the combustion chamber and never touches the intake valve. Any oil vapor that gets through the PCV and rides into the intake tract deposits on the back of the intake valve and slowly bakes into hard carbon under heat. Over time, that carbon buildup restricts airflow and causes cylinder-specific misfire codes, hesitation under load, and cold start roughness. The failure cascade on a direct injection engine with a bad PCV is the same 6-symptom pattern as the port injection cascade, plus a 7th symptom: accelerating intake valve carbon buildup that costs several hundred to over $1,000 to clean at a shop with a walnut shell blast or an equivalent chemical treatment. This is why keeping the PCV valve functioning on a modern DI engine is more consequential than on the older engine designs. The downstream damage compounds faster. A note on driving pattern, because it affects PCV service life significantly. Short trips where the engine doesn't reach full operating temperature, under about 10 minutes of drive time, leave water vapor and unburned fuel in the crankcase that never boil out. That water and fuel condense with the blow-by residue and accelerate sludge formation inside the PCV valve. Cars driven mostly on short urban trips typically need PCV service every 50 to 60,000 miles. Cars driven mostly on highway trips can go 100 to 120,000 miles without service. This is one of the categories where severe service in your owner's manual actually means something concrete. Here's what happens when the PCV valve fails. And the failure mode is almost always the same. The valve doesn't break in a dramatic way. It just gets clogged. Over time, the crankcase blow-by carries with it oil vapor. Some of that oil vapor makes it all the way through the PCV valve and into the intake, where it burns in the combustion chamber. But some of it condenses on the way through and slowly builds up a coating of black oily sludge on the inside of the PCV valve itself and on the intake side of the valve seat. Over enough miles, usually somewhere between 80,000 and 150,000 on most engines, and much sooner on engines that see a lot of short trips where the oil never gets hot enough to burn off water and fuel contamination. That sludge builds up to the point where the check valve either sticks partially open or gets restricted enough that flow drops significantly. Once flow through the PCV valve drops, the pressure balance inside the crankcase changes. Blow-by continues to enter the crankcase, but it can't escape through its normal route. Pressure rises, and now the failure cascade begins. Symptom 1. Oil starts pushing past whichever seal or gasket has the weakest surface pressure. Usually that's the valve cover gasket first. Sometimes the front main, sometimes the rear main. Oil leaks appear where none were before. Symptom 2. Some of the trapped blow-by finds its way through the intake side of the PCV plumbing anyway, pushed by crankcase pressure instead of pulled by manifold vacuum. That gas carries oil vapor with it. The oil vapor deposits on everything downstream in the intake tract. The throttle body plate, the intake manifold walls, the intake valve backs, the mass airflow sensor element. Symptom 3. The MAF sensor's platinum hot wire element gets coated with a thin oil film. The MAF now reads low, measuring less airflow than is actually entering the engine. The ECM compensates by commanding less fuel. Combustion runs lean. Symptom 4. The exhaust oxygen sensor sees the lean condition and tells the ECM to add fuel back. Long-term fuel trim on bank 1 starts creeping up, plus 5%, plus 10%, plus 15%. Eventually, the trim runs out of room to compensate, and the ECM sets a P0171 lean code. Symptom 5. At idle, the small unmetered air leak that a stuck-open PCV valve represents makes idle unstable. RPM hunts. The car surges gently at stoplights. Symptom 6. Oil vapor being pushed backward through the crankcase ventilation system finds its way to the fresh air side, the breather hose that connects the valve cover to the intake tract upstream of the throttle plate. That's where the smell inside Chelsea's cabin was coming from. Oil vapor migrating out through the valve cover breather and into the general engine bay air, then being pulled into the HVAC system's fresh air intake. 1 $9 clogged check valve, 6 apparent symptoms. Now, why do shops miss this? Because the same flat-rate diagnostic tree that cost Chelsea $2,400 is running on your car this morning too. And here's what the shop's service advisor won't volunteer at the counter. The tree follows the codes first. A P0171 code has a documented troubleshooting path in most professional diagnostic databases, and the path typically starts with fuel trim analysis and works through fuel pressure, MAF sensor condition, and vacuum leak testing before it gets to the PCV valve. The PCV valve is on the list, but it's not at the top. At the same time, the shop tech is paid by the flat rate labor hour, and the fastest way to close a repair order is to replace parts that are commonly wrong. Chelsea's tech replaced the MAF first because MAFs are commonly contaminated on high-mileage cars. When the code came back, he cleaned the throttle body next because throttle bodies are also commonly deposit fouled. When the rough idle persisted, he resealed the valve cover gasket because the visible oil at the gasket line was a real finding. Each individual step was defensible. The problem was that none of them addressed the actual root cause, and the root cause was continuing to push oil vapor through the intake tract, even after each individual repair. This is where the compilation videos that talk about PCV do get one thing right. They point out that on many diagnostic trees, the PCV is checked last or not at all. What they usually get wrong is the framing that this is because shops are dishonest. They aren't, most of the time. It's because the diagnostic tree is optimized to hit the most likely single-cause faults first, and PCV failure looks like 6 different faults simultaneously, which the tree treats as unrelated. The way you break out of that trap is by testing the PCV first, before you touch a single other component. That test takes 15 seconds and costs $0. Read the OEM service bulletins on any of these engines, and it's right there, buried on page 47, but there. The test. 15 seconds, $0. Warmed engine, idling in your driveway. Warm the engine to operating temperature. Coolant temperature above 180 degrees Fahrenheit. Let it idle. Pop the hood. Locate the oil filler cap on the top of the valve cover. Slowly and carefully, because if the engine is truly pressurizing, you'll get a light blowback of oil vapor. Lift the oil filler cap and observe what happens at the filler neck opening. On a healthy engine with a functioning PCV valve, you should feel a very light suction at the opening. The manifold vacuum being applied through the PCV routing should be pulling air down through the filler neck into the crankcase. Set the cap loosely back on the opening. It should sit slightly askew and stay put, held down by that faint negative pressure. On an engine with a failed or stuck-open PCV valve, you'll see the opposite. Instead of suction, there's a visible, pulsing outflow of oil vapor from the neck. The vapor has that characteristic warm oil smell. If you set the cap loosely back on the opening, it will lift and rattle from the outflow pressure. In severe cases, you can actually see a small cloud of vapor rising from the neck continuously. That's the 15-second test. If the outflow is present, you have a PCV failure. If the suction is present, look elsewhere for your lean code and your rough idle. A second confirmation, in case the oil cap test is ambiguous. Pull the air filter housing lid, usually 2 clips or 4 screws. Look at the underside of the air filter itself and the intake tube walls between the filter and the throttle body. Is there a black, oily film there? Any streaking? Any visible oil mist deposit? If yes, that confirms oil vapor is being pushed backward through the fresh air breather side of the PCV system, which only happens when crankcase pressure has exceeded normal. Both tests together will identify a failed PCV valve with better than 90% confidence, and neither requires a scan tool, a smoke machine, or a diagnostic bay. One additional note on the oil cap test, because there's a middle ground result that trips people up. Some engines, especially older high-mileage engines with worn piston rings but still functional PCV valves, will show a slight neutral pressure at the filler neck rather than clean suction. That's not necessarily a failed PCV. It can be a symptom of increased blow-by from ring wear that's still within what the PCV can handle. To distinguish the two, run the test a second time immediately after a hard highway pull, when blow-by is at maximum. If the PCV is functioning, you'll still see suction at the cap after high-load driving. If the PCV is failing, the outflow becomes obvious under load conditions. The healthy engine version of this test should give you clean suction across all engine states. For anyone with access to a low-pressure manometer or a magnehelic gauge, the professional version of this diagnostic is measuring actual crankcase pressure at the oil filler neck. Healthy modern engines run somewhere between 1 and 3 inches of water vacuum in the crankcase at idle. Failing PCV systems will read positive pressure, sometimes as much as 4 to 6 inches of water. Most home mechanics won't have a manometer, but if you're deep into diagnostics on a particular engine, the tool costs about $40 and settles arguments about borderline test results conclusively. Where the PCV valve lives on your vehicle is the next question, and this is where it gets platform-specific. On some engines, most classic pushrod V8s, most older Toyotas, many Hondas, the valve is right on top of the valve cover, held in with a rubber grommet, and you can pull it out with pliers in about 30 seconds. On other engines, especially newer 4-cylinders and modern V6s with plastic intake manifolds, the valve is mounted underneath or inside the intake manifold, and you have to remove parts of the intake plumbing to access it. On Chelsea's Subaru FB25, the valve is on the driver's side of the intake, near the throttle body, accessible from the top of the engine, but requiring a Torx driver and about 15 minutes with the intake tube pulled to the side. Some German engines, Volkswagen EA888, BMW N54, and N55, use an integrated crankcase ventilation module that isn't a simple valve you can replace by itself. On those platforms, replacing the whole module is a $200 to $500 part and labor job, but the failure mode is the same clogging, and the diagnostic test is the same oil cap check. The general rule is that if you can find your engine's factory service manual, all data, Mitchell, forum posts pointing to specific FSM pages, the PCV location is documented. If you can't find it easily by inspection, look it up before you order parts. 4 platform-specific examples worth mentioning because these come up a lot in the shop. On the Toyota 2AR-FE, the 2.5-liter 4-cylinder, and Camry, RAV4, Highlander, and several other applications from 2010 through 2017, the PCV is on top of the valve cover on the passenger side, held in with a rubber grommet. Pull it straight up with pliers. 2-minute job. Toyota part number typically runs about $8 to $12 at the dealer counter. On the Chevrolet Ecotec LNJ and LTG engines, turbocharged direct injection 4-cylinders in Cruise, Malibu, and various current GM vehicles. The PCV is integrated into the valve cover as a diaphragm assembly. It's not a replaceable valve on its own. You replace the entire valve cover. $60 to $90 for the aftermarket cover, 1 to 2 hours labor. The failure mode is the diaphragm tearing rather than sludge clogging, but the symptoms are identical. On the Ford 5.0 Coyote engine in F-150 and Mustang from 2011 onward, the PCV is on the driver's side valve cover near the front, easy access from the top of the engine. $12 to $18 for the valve, 20-minute job. On the Subaru FB25, which is Chelsea's engine, the 2.5-liter naturally aspirated 4 in Outback, Legacy, and Forester from 2011 forward. The valve is on the driver's side of the intake manifold, near the throttle body area. Requires pulling the intake tube back and using a small Torx driver. 15-minute job, $12 valve. If your engine isn't one of these four, the same principle applies. Look up the FSM, confirm the location, buy the correct part, plan for 15 to 45 minutes depending on access. Chelsea's Subaru, the follow-up. I pulled the old PCV valve after doing the oil cap test. Heavy outflow, visible vapor pulsing at the filler neck. No question. The valve came out coated in a thick black tar-like film that had partially blocked the check valve seat. When I shook it, it rattled inconsistently. The internal spring-loaded plunger was sticking. That's exactly what a failed PCV valve looks like. $12 for a new Subaru spec PCV valve at the parts store. $6 for a new gasket. About 45 minutes of labor, including doing the oil cap test both before and after to verify. Total bill, $80. Chelsea's rough idol was gone by the end of the parking lot on the way out. She called back 3 weeks later. The check engine light hadn't returned. LTFT had settled back towards zero. The cabin oil smell was completely gone, and her oil consumption between changes had dropped from about a quart every 1,200 miles to essentially zero measurable consumption over the next tank. $2,400 for a MAF she didn't need, a throttle body clean she didn't need, and a valve cover gasket she probably did need, but that never was going to fix the actual complaint. $80 for the part, the gasket, and the labor that actually solved it. Same car, same code, same rough idle. The only variable was which shop ran the 15-second test first, and one shop never did. Host anecdote, because preventive is worth mentioning. Here's what 15 years under hoods tells me, and the failure pattern on Chelsea's Subaru proves it every time I see the same cascade in the shop. My own truck, 2020 Toyota Tacoma, 3.5-liter 2GR FKS V6, 68,000 miles, Portland, Oregon. This engine has a documented service interval on the PCV valve at 80,000 miles per Toyota's maintenance schedule. But I like to check it a bit early because Portland gets a lot of cool, wet weather and short trips, which are hard on crankcase ventilation systems. I ran the oil cap test at 68,000. Result was borderline. Not a clear suction, not a clear outflow, more of a neutral pressure with occasional puffs. That's the pattern of a PCV valve that's starting to get restricted but hasn't fully failed yet. Pulled the valve. Yes, the plunger was sticking intermittently and the check valve seat had a thin oil film starting to build. $14 for the Toyota spec valve, about 20 minutes to swap. Oil cap test after. Clean suction pattern. Cap holds down under negative pressure. Done. That's the preventive angle on PCV service. If you're past 60,000 miles on a normal-duty vehicle or past 40,000 on a short-trip heavy vehicle, run the oil cap test. If the result is borderline or worse, replace the valve. It's cheaper than any of the downstream symptoms. Wrap. 3 action items. 1. If you have a rough idle, a lean code, unexplained oil consumption, an oil smell in the cabin, or a check engine light that keeps coming back after MAF or throttle body work, do the oil cap test on a warm running engine before you approve any more repairs. 15 seconds, $0, tells you whether the PCV is the actual root cause. 2. Pull your air filter and inspect the intake tract for oil sheen. If the filter or the intake tube walls show a visible black oily film, that's confirmation of PCV backflow. If the filter is clean and dry, the failure cascade is probably not PCV. 3. If either test is positive, replace the PCV valve. Match it to your manufacturer's part number. This is one component where OEM, or true OE equivalent, matters, because the spring rate on the check valve is calibrated to the engine's specific manifold vacuum profile. A generic aftermarket valve with the wrong spring rate will either flow too little or too much, and either creates its own problem. Most parts stores carry the correct part for common vehicles for $9 to $15. On less common engines, it's an online order for $20 to $30. If a shop has ever billed you for a MAF sensor, a throttle body clean, or a valve cover gasket, and your rough idle stayed exactly the same, drop a comment with your vehicle year, make, model, mileage, and what got replaced. I read the comments through the week. If a pattern shows up on multiple viewers with the same platform, I'll pull that into a follow-up walkthrough for that specific engine family. Chelsea has her Outback back on the road, with no complaints, no returning check engine light, no cabin oil smell, no oil consumption to speak of. $2,400 in previous defensible but wrong repairs. $80 for the 15-second test and the $12 valve that actually finished it. If you take one thing from this walkthrough, take that ratio. That's what a diagnostic tree that skips the cheapest test first looks like on your bank statement. My Tacoma is running clean. The next video I'm putting together is on the mass airflow sensor specifically. How to read live MAF data on a scan tool to distinguish a genuinely bad MAF from an MAF that's just contaminated by PCV backflow. Because that distinction alone would save a lot of drivers a lot of unnecessary MAF replacements. See you then.